Hello, so in this video we're going to start by kind of introducing the main elements that we kind of need, the building blocks if you like, to start talking about this idea of filtration. That's where I left the last video off. You know, if you remember, we were looking at martingales, and I said that, you know, dealing with martingales in the discrete case is fine, it's relatively easy-ish. Okay, but as soon as we try and deal with martingales with continuous cases, that's where it becomes more complicated, and that's where we have to use something called filtration. And effectively, a filtration is just a flow of information up to some time point. Okay, but before we can, you know, so that's where we want to end up. We want to end up starting to talk about filtration. But before we do that, we're going to have to start, you know, introducing some new ideas, basically. And this is what we're going to start doing in this video. Okay, so basically, at the centre of the theory of financial mathematics, we've got this thing called stochastic calculus. Stochastic calculus. Okay, and the reason being is because the processes that are kind of dealt there. For example, I've alluded to it before. That, you know, one of the processes that kind of financial mathematics follows, say like a share price, will follow something like a Brownian motion. We're trying to differentiate. You know, differentiation is really useful because it talks about the rate at change. So how quickly something changes. Okay, and that kind of lies at the heart of, you know, a lot of things to do with finance. And so basically we want to try and differentiate this process. Well, obviously it's a continuous process, and the whole point is that if we zoom in on this, it's still going to be infinitely jagged. Whereas you see, normally when we have a function, we zoom in, it becomes like a straight line, and we can find the derivative of that because it's just the gradient of a straight line, okay? But because now we've got a case where it's jagged, we can't then differentiate it, so we can't talk about the rate of change. So therefore we have to introduce this idea of probability associated with calculus. In order to start talking about, you know, in order to start talking about how, you know, the rate of change of things. Okay, so at the centre of financial mathematics is this thing called stochastic calculus. Now we're going to start exploring kind of the rudiments of this topic, and kind of how it interacts with the financial derivatives. But we are going to kind of omit some of the more technical details. We're not going to get bogged down in the more technical details. You know, if you want to look in the more technical details, go elsewhere, go and find a book, or go and find something on the internet, and, you know, learn about it, or take a stochastic calculus module. But in this topic, we just want to get what we want out of it. We don't want to get bogged down on the kind of details. We just want to get the main gist of what's going on, so then we can start talking about kind of future things. So basically, what we're going to be looking at now is this thing called a discrete. We're going to look at, you know, the discrete case at the moment. Okay, so we're going to look at discrete case. Okay, we're going to start there because that kind of makes sense that we start looking at the discrete case. Okay, so what I wanted to do is I want to try and build up a picture of your mind, and we're going to start talking about this thing called a probability triple. Okay, and we're going to start talking about this thing called Sigma-Algebra, which really is a new way of talking, I suppose. Kind of, it's algebra, but it's a bit like S-algebra. I suppose the S stands for stochastics. Okay, so it's kind of like statistic algebra, if you like, stochastic algebra. So Sigma-Algebra it's called. Sigma-Algebra. Okay, and the first thing which I'm going to start talking about in order to kind of introduce this idea. So these are kind of, I'm just outlining all the ideas that we're going to kind of hopefully come on to within the next few videos. And first things first, I'm going to start talking about this probability triple. Now, what I want you to imagine is that we have a house. Okay, and so we've got a house going on. There we go. There's a nice little house here. Okay, we've got a roof going on, a little bit of a chimney. So there we go. So here we go. We've got a house basically, and I want you to basically say, well, okay, everything that happens in this house, everything that can possibly happen. I'm talking everything that can possibly happen within this house. Okay, will be called, let's call that sigma. Okay, so let's call that sigma. So everything, all the possible outcomes that can happen in this house. So for example, you know, a book will fall off the shelf, or I'm talking about, you know, a kitchen catching fire, or I'm talking about the food in the fridge going off. I'm talking about everything, every single thing that can possibly happen within this house, every possible event which can possibly happen in this house. I want to call that sigma. So this is all events that can happen in our house. and I want to call that sigma. Okay, and each event which happens in that house will have a probability associated with it. So I'm going to call that P. Oops. I'm going to call that P. Okay, and that's the probability that is associated with each event happening. So the probability associated with each event happening. So probability associated with each event happening. Okay, so the probability with each event happening, I'm going to call that sigma. Okay, and then finally, what I'm going to have as well is this thing called F. Okay, which is a collection. Essentially, it's a collection of everything which can possibly happen in the world. I'm not just talking about in the house. I'm talking about in the world. So absolutely everything that can happen in the world. So all events that can happen in the world. In the world now, so not just in the house. I'm talking about in the world. So this is F, if you like, is the world. Okay, so everything which can happen in the world. But obviously the house is just a small little section of that world. Okay, and that's just defining all the events that can happen in the house. Okay, so therefore I can form a probability triple from that. So I've got sigma, which is all the events that can happen in the house. Okay, I've got F, which is all the events that can happen not just in the house but in the whole world. Okay, so there'll be some things that can happen in the world that can't happen in the house. Okay, so obviously F has got to be bigger than sigma. Okay, and then also we've got the probability. So all of the events that happen in the house, I'm going to define by some probability. I'm going to define by some probability. I'm going to call that P. Okay, so so let's kind of so basically what we can say is that F, which is all of the events that can happen in the world, is a Sigma-Algebra. Okay. And we can define it as follows. So basically it's a Sigma-Algebra, and we can define it using kind of statistic processes. So basically, here we go. They come from probability. That's why it's called stochastic algebra. So basically we can say, that... Okay, so basically what I want to say first of all is that sigma, so remember everything that can happen inside our house, sigma must lie within all of the probability, all of the things that can happen in the world. Yeah, that's fairly obvious. That everything that can happen inside this house, okay, is just a small section of everything that can happen in the world. So, for example, a tree could fall down. There might be a tree, for example, in the outside world, right? And that tree could fall down. But obviously, that isn't going to happen inside my sigma, inside my house, okay, because there's no tree inside my house, for example. So, obviously, sigma is smaller than everything which can happen in the world, okay? So, F is in actual fact much bigger than sigma, much bigger, because F covers everything that can happen in the world, whereas sigma only covers everything that can happen inside my house. Now, there's a lot of things that can happen inside my house, but, F is obviously much bigger because it covers the whole world, okay? So my second identity is that A, so A, let me just define A. So A is an event. A is just an event that can happen, okay? An event which can happen, obviously it will lie within F, okay, because it's just an event which can happen. Okay, so A, so if A is a member of F, so A lies within F. So A is just an event which can happen. So obviously F defines all of the events that can happen. So A falls within that circle, if you like. So then that then implies that I can also have sigma minus A, okay, is a member of F. So basically what this is saying is that the complement, okay, complement. So, I've got my, if you like now, I'll just change it up a little bit. This is my house, okay? I've got all of the events that can happen in there. I've got all the events that can happen in there, so I'm going to call that A. Okay, but I've also got the events which can't happen in there as well. I've also got the events that can't happen in there as well. So this is like my event A. This is my sigma. Okay, all of the events that can't happen in there are defined by this bit. Okay, so this is sigma minus A. Okay, so if you like, say for example, if I have a dice in my house, okay, I can talk about the probability of getting a 4 on that dice, but I can also talk about, so this is the probability of getting a 4 on that dice, but I can also talk about the probability of not getting a 4 on that dice as well. So I can talk about the opposite events as well, because if I've got an event, I can also talk about the opposite events, and those opposite events will also lie within F, Okay, so hopefully that makes a bit of sense. And my third and final identity is that if I have, say, all my events, okay, all of my events, I'm just going to denote them by AN. So, for example, A1, A2, they're all separate events. A3 is another event, A4 is another event, okay, and I can keep going right the way through to all of the events that can happen in my house. This is all the events that can happen in my house, AN. Then obviously that's got to be a member of F, okay, like I had before. AN's got to be a member of F, but I'm just using a subscript N to denote all of the events that can happen in my house, not just one event. This is just one event up here. Now I'm denoting all the events that can happen in my house, okay? Then that implies that the union, which I'm going to denote by a capital W, of all of my events, so from 1 to infinity, or yeah, from 1 to infinity, all of the events that can happen in my house must also be within N, within F. Okay, so in other words, if one event lies within F, then all of the events must also lie in F. That's kind of a bit of an obvious one. So union is just another event. Okay, so basically what I'm saying here is that the union, this is all my events down here. So I've got all my events down here that can happen inside my house. I've got all the events that can happen inside my house. Okay, well, if I take the union of them, so in other words, I put them all together, then fairly obviously the union of them is still going to be inside F. That's kind of obvious, right? Because F defines all the events that can happen in the world. So if I take all of the possible events that can happen inside my house, then if I kind of put them all together, then that's still going to be within inside F. Okay, because then I can so basically what I'm saying is that I can talk about the probability of A1, okay, so the probability of one event, and I can also talk about the probability of A2, okay, but what I can basically say now is because I can take the union of them, and that's still going to be inside F, then basically I can talk about the probability of A1 happening or A2 happening. Okay, so I can talk about the probability of A1 happening or A2 happening. Right, probability of A1 or A2 happening, and the notation for that is A1 union A2. Right, so that's kind of where that comes from. Okay. Another kind of nice thing. Say if we have an event, let's call it B. Okay, or no, actually let's stick with A. So this is an event, okay, which happens, and because A lies within F, so any event that lies within F, we can say that A is F measurable. So F measurable. So in other words, it can be measured using F, or measurable anyway. So A is basically F measurable. We say that. Okay. Now we've talked about events happening and whether which space they lie within, but we haven't actually talked about any of the probabilities as such. Okay. So the probability P. So we've talked about sigma. We've talked about F. And we've talked about the events which happen within F. Okay, and sigma, but we haven't actually talked about P, and P must follow some of these axioms. So here are the axioms. Okay, it's a probability. So first things first, it's kind of the standard one, that basically the probability of any event happening must lie between 0 and 1. So the probability of any event happening must lie between 0 and 1. So that's kind of normal, okay? We can't have, for example, a probability of 1.5 or a probability of 3. It's got to be a probability of between 0 and 1, okay? Or we can convert it into percentage, or we can convert it into a fraction, but it's basically got to lie between 0 and 1, okay? Now, 2, the probability of the sample space. So remember the probability of my house. So anything. So we're inside a house. The probability of something happening within inside my house, because I'm only considering my house, has to be 1. So the probability of all the events which lie inside my house, all of the events which happen inside my house. Okay, the probability of all of those events which happen inside my house, if I put them all together, then therefore there has to be certainty there, because there has to be certainty that something's going to happen. So therefore the probability of my sample space of my house is going to be 1. Okay. Okay, then suppose we have all these kind of all these events again, like we had before. So we have all my events which happen inside my house, AN. Okay, and then let's talk about the union of them. So I think I've spoken about this before, or just above, but I'll just go through it again just in case it didn't quite sit in. So in other words, because I've got all of my events, and they're all disjoint, they're all basically disjoint events. So basically, my book falling off the shelf is totally separate to, say, I don't know, my kitchen catching on fire, or me burning the toast. Okay, my book falling on my book falling off the shelf is totally different to my me burning the toast. Yeah, this is kind of like a bit of a I don't know, if you're following my example, well done. I hope it makes it a little bit clearer rather than talking about things generally and stuff. I think just talking about it in this example, I think, to me it makes sense at least. If it makes sense to you, then great. If it doesn't, then I apologise, but hopefully you can follow what I'm writing down anyway. Okay, so basically here what I'm saying is if I put all my events that can happen in my house together, okay, then that's just going to be equal to the sum of the probability of all my events. So from n equals 1 to infinity. And that kind of makes sense. So basically what I'm saying here is that the probability of, say, A1 or A2, okay, so I've got two distinct events, A1 and A2, right? The probability of A1 or A2, well, that's just, if they're distinct, then I can just say that's the probability of A1 plus the probability of A2 happening. Okay, so the probability of A1 happening or A2 happening, two events, probability of either one happening, so either A1 happens or A2 happens, is the probability of A1 plus the probability of A2, okay? And the way which we write that using statistics is A1 union A2 is equal to probability of A1 plus probability of A2. And that is all I've got written down. That's all I've got written down here. So here's my union, and here's my sum, and here's my sum.